Hello and welcome to the Spark and Reachy Mini photo booth playbook video. We will give an overview of the playbook, go through the instructions to set up the hardware, deploy and run the application, and we will also see how developers can easily extend the playbook based on their needs. In short, this playbook shows how to run a multimodal agent locally on DGX Spark with multiple AI inference models. We connect DGX Spark to the Reachy Mini robot by Hugging Face, which acts as a front end of the multimodal agent. The application is a fun and engaging photo booth experience where the robot conversates with the user, asks a few preferences, then takes a picture of the user and transforms them into whatever they wanted. And finally, the robot shows the generated image in a UI. The playbook is running multiple AI models. They are orchestrated by an agent built with the NeMo Agent Toolkit framework from NVIDIA and by an interaction manager service which handles the communication between the various services and the state machine of the robot. In particular, we use GPT-OSS 20 billions for the LLM, we use NVIDIA Riva for speech-to-text, Kokoro for text-to-speech, Detectron 2 and ByteTrack to track the users, and finally we use Flux1 Context Depth to generate the images starting from the input image. In addition, we run a UI on the browser which is also running locally on the DGX Spark. On the UI, we show some tools and animations to display the status of the robot, and of course we also show the final generated image. During the interaction, the robot sees and hears the users, talks to them, and is animated to show its status, whether it's listening, talking, generating an image, thinking, and so on. First of all, let me show you a quick video of the running playbook.
Hello, Reachy.
Power nominal. First, what kind of setting or background would you like for your photo? For example, a beach, a space station, a fantasy forest, or something else?
Let's do a desert town.
Fantastic. I'll wave my wand and take your photo, strike a pose, and freeze.
Wanna join?
Ready to transform your desert adventure. Done with the image.
That's nice.
Check it out, you're now a bold comic book cowboy standing in a dusty desert town, hat tipped, boots kicking up sand, all in vibrant, bold lines that pop like a classic comic panel.
Alright, so let's see how you can achieve that. In the overview page of the playbook, we can start from the prerequisites. Of course, you will need the NVIDIA DGX Spark and the Reachy Mini robot from Hugging Face. In our case, we use the Reachy Mini Lite robot. We also connect a monitor, a keyboard, and a mouse to the DGX Spark to being able to develop and run the application. The DGX Spark has the official DGX Spark OS image, which includes the required utilities like the NVIDIA drivers and so on. Make sure to connect the DGX Spark to the internet. In order to run the playbook, you also need to have an NVIDIA NGC personal API key as well as a Hugging Face access token. We will see later how to do that and why this is needed. This is an image of how the final hardware setup should look like. And keep in mind that in order to run the playbook for the first time, it will take about 2 hours. Most of the time is needed to download the images and the models. Now that we've seen the prerequisites, we can jump to the instructions. First of all, we need to clone the repo. We recommend users to be in the Docker group to avoid having to run the commands with sudo. You can check with this command whether you have the permissions and are in the Docker group. As you can see, I get a permission denied error, so I can run the follow-up command to fix it. Now, with the final command, we can clone the repo from the public GitHub. Alright, as a next step, we will create our environment. So we need to fill this environment file with some environment variables. we have an example file that we can use and copy into the M file with this command here. We can now visualize the environment file. As you can see, we have marked in the file with the placeholder fix me places where you have to fill in your environment variables. Like I mentioned before, you need to have an NVIDIA API key. This is required to access assets on NGC like the NVIDIA names. And we also require you to have a Hugging Face token. This is required to access the models on Hugging Face. So let's start with NVIDIA API key. You can log into NGC, and then by going into Setup, you will end up on this page. Then Generate API key. And finally, up here, Generate Personal Key. You can give the name of the key, an expiration, and for services included, pick NGC catalog. Then go on and generate your personal key once you have chosen the name. The key will start with NV API, and you can fill it in here. Now for the Hugging Face token, you can log in into the Hugging Face website and then go to Settings here under your profile name, Access Tokens, Create New Token. You can pick Read for token type, give it a name, and create your token. This token will start with HF, and you can fill it in here. In addition to creating the Hugging Face token, in order to run the playbook, you will be required to review and accept the FluxOne Context Dev and FluxOne Context Dev ONNX license agreements and acceptable use policy. So simply click on these links, and you will be prompted the license to review and accept. I've done it already for my profile. Finally, you can see here that there is also this variable called external min.io base URL. We describe it here in the instructions. By default, you can leave this unchanged. In case you want to show in the UI, in addition to the generated images, also the QR codes of the generated images for the users in your local network to download them, then you will have to change this variable. We do not cover these steps in this video. All right. Once you have filled in the variables, you can save and close the file. The next step is to set up Reachy Mini. We have already covered at the beginning of the video how the hardware setup should look like. Once again, make sure Reachy is plugged into the power. You will see a LED light at the base of Reachy. And also make sure that Reachy is plugged in with a USB-C cable to the DGX Spark. You can check that the Reachy robot is correctly detected as a device by running this command in your terminal. You will see a device showing up here if everything is set up correctly. Also, it might happen that the volume of Reachy is low, so make sure to run this script to ensure the speaker of Reachy can reach the maximum volume. All right, now the next step is to start the application. First of all, we have to sign in into the NVIDIA container registry. So you can run this command. You will be asked for a password, and this is the same NGC personal API key that you have created before and added to the environment file. So I'm adding my key now, and as you can see, the login succeeded. Once that worked, we can start the Docker compose app command. This command will pull and build the container images and download the model and the artifacts. Keep in mind that the first run will take between 30 minutes and up to 2 hours. This depends on the internet speed. The following runs will usually complete in less than 5 minutes. Sometimes, when running the playbook for the first time and downloading all the models, the image generator might fail to start for the first time. In that case, simply rerun the Docker compose app command. And now that the command has succeeded and all the images are up and running, you can open the UI in your browser, for example, using the pre-installed Firefox and clicking on this link. and simply talk to Reachy to wake it up. Hello, Reachy.
I've got a good feeling about this.
Now let's look at how you can customize the photo booth application and develop new tools for it. For this, go to the Development tab of the Playbook. First of all, in order to install all the necessary packages to use the Python development setup of the repository, run this command. Then install UV by following the instructions here. I will run this command. And then run this command to generate the Python virtual environment. Now it is time to get familiar with the build and development process. Let's open VS Code for that. Every folder that ends with service is a standalone Python program that runs in its own container. At the root of the repository, you will find a Docker Compose YAML file which defines which services run and their configuration. By running the Docker Compose app command with the watch flag, you can start the application, enabling code hot reloading for all the Python services. Whenever you change some Python code in the repository, the associated container will be updated and automatically restarted. And now that the development environment is set up, you can easily customize the application and the parameters of each service. Each service has a README file as well as a configuration Python file with detailed configuration options. Keep in mind that the Compose YAML file of each service might override the configurations in the Python file. For example, here you can see where you can customize the system prompt of the agent service. After having seen how to customize the configuration parameters, we will now see how you can extend the photo booth playbook with adding a new tool. As an example, we will add a functionality to the robot to scan the room by playing a scanning animation whenever the user asks it to do so. For such changes, you will most likely have to change the core services, which are the agent service and the interaction manager service. The agent service is the Nemo Agent Toolkit agent. This is where we will add the new tool. And the interaction manager service is the service which manages the events and the state machine of the robot. You often have to modify both because they need to be in sync. So let's go to VS Code for this. I have prepared the necessary changes for adding the new scanning tool, and I will give you an overview of those. In the photo booth YAML configuration file of the agent service, we define the new tool. We call it the look around tool, and we add it to the configuration together with the other tools for the agent. Then we implement the tool. We create a new file called look around in the agent service. Here is where we actually implement the tool. The base functions and classes all come from the Nemo Agent Toolkit, and I suggest you check out the Nemo Agent Toolkit documentation for this. Here we implement the tool configuration class. These are the tool properties and configurations. For example, the already existing image generation tool might have the number of steps needed for image generation as a property here. In this case, for our new tool, we do not need any special configuration and we can leave it empty. Then here is where we define the tool input parameters as per design of the Nemo Agent Toolkit framework. These are the parameters that the LLM generates when calling the tool. The main parameter in our case is the message string down here. This is where we instruct the LLM to create the robot utterance to say when it's scanning the room. There is another parameter called action UUID. You can leave this empty. Without going too much into details, in our framework we have the concept of actions which have an ID. For example, a tool call is an action, and we use the ID to identify the action and propagate it through the system. For example, we use this to know when a text-to-speech message has started and has finished playing. This is the only field of the input that the LLM doesn't generate. Our framework indeed automatically generates these action IDs. Then we go to the tool implementation and logic. Here is where we register the tool. The main logic goes into the ARun function from the NeMo Agent Toolkit framework. In our case, the logic is very simple. We just coordinate between the agent and the interaction manager, which again is where the state machines of the robot are, including events from services and animations. We coordinate with the helper function wait for acknowledgement. We will modify the interaction manager to trigger the scan animation for this new scanning tool, and at the end of it, send a message to the agent to signal it is done with this animation, with the action ID as parameter. So the function wait for acknowledgement is a function that waits for the message of the tool being processed with that input action ID. Then, finally, here we create the return statement, which is added by the NeMo Agent Toolkit to the history of the agent. To conclude the agent implementation, we import the tool in the init of the tools in the agent service. Now we can go on with the implementation of the new tool in the interaction manager. We start by adding the tool in the configuration file. In our application, multiple tools can trigger the same action. In this case, the look around tool will trigger the scan action. You can add other tools that perform the same action. For example, one could think of a search tool. And now we will implement in the main file of the interaction manager the logic of the scan action. We get here the tool that triggers the scan action from the configuration we have done before. Then, in a loop that processes every tool it receives, we trigger the scan event when we get the look around tool. Notice that we get the input message of the tool, the message generated by the LLM as we have seen before when implementing the tool in the agent, and we pass it as parameter of the scan event. Finally, in the photo booth bot file of the interaction manager, where we have the state machine, we need to adapt it to receive the scan event and change the state. First, here we add the scan state. Then we need to create the transitions. Here we add the transition from scan to find the user. Find user is a default state of the original photo booth application, which we use often, and it is where the robot looks for the user before speaking or listening. By adding this transition from our new scan state to the core find user state, we make sure we can come back to the original photo booth logic after playing our new scanning animation. Then, here, we create the new main transition to go to the new scan state, which will be triggered by the scan trigger event we looked at before. In our case, the source state is the think state, because this is where the robot will be when processing the tool call to look around. Finally, we need to implement what to do once the transition is done and we are in the newly created scan state. We gather the message as input from the tool, and we request a speech generation to the text-to-speech service with this function that sends a message in Kafka. We also request a talking animation that moves the head when the robot talks. As a result of all of this, the robot will say something like, "I'm scanning the room," while moving its head. We then wait for the animation and the speech to finish, and then we trigger the scan animation and wait for it to finish before returning. So let's see how our new tool works with Reachy. I will save the changes. As you can see, the services will restart automatically, thanks to the code hot reloading functionality. And now let's try the new tool. Hey Reachy, wake up.
I love the smell of fresh code in the morning. Greetings from the NVIDIA booth. I'm Reachy, your AI photographer of the day. Ready for some photo magic? Say yes and let's begin making something awesome.
Can you scan the room for me?
Let me scan the room.